Hello. Thanks so Matt for helping download the slideshow. So I'm Joshua, and I'm going to talk about Android malware obfuscation, and I have a lot of disclaimers first. So this is the subtitle, and who am I? I was writing software for around 5 years, just, engineering things forward, and now am reverse engineering things. And this is my opinion. I deleted all corporate data from my mind, so this might be not the opinion of who I work for. So I use a lot of sources for this, so I wanted to cite some of them. There's a lot of good information in this book. The Android Malware Handbook has multiple authors, and so it just has a lot about Android malware analysis, so it's very helpful. Okay, so here's what we're going to talk about. Like different categories of Android malware, malware that's not obfuscated, how to obfuscate it using Java code, how to obfuscate it using native code, and then there's a particular obfuscator called Armor that we are going to talk about. All right, what is Android malware analysis? First, we'll say what it is not. It's not vulnerability research, and it's not pen testing, even though that's super fun. You're going to be wasting a bunch of time if you're trying to do that because the users just need to know if their data is going to get stolen. They don't really care if there is a bug in the malware. So just try to focus. We're going to focus on like when we're analyzing malware, what are the major data types that are stolen? Like their phone number is stolen, their screenshots are stolen, anything like that. And because there's limited time, you can't look at like every single line of code. There's a library in Android. It's called Emoji Compat, which is super great. I've reverse engineered that many times, but that's not where the malware is. That's just the emoji library, but it doesn't necessarily say that on every file because file names get randomized. So make sure you're reverse engineering, the important parts of the code. Okay, so here's general principles of malware analysis, especially for Android. So you might have a decoy app, like you could try to find 0 day and like say, how can we get their contacts with no contacts permissions on Android? But it's a lot easier, like just make a contact app and publish it, and then people will install it, and then they'll ask, can I have permissions for your contacts? And they'll say yes. So that's a lot easier. And then you're gonna think like, what data do I want to steal? Their contacts, their screenshots, whatever. And then you're gonna think, how am I gonna exfiltrate it? And then you're gonna think like, how can I load more code that can do more bad stuff that's not in the first stage, so it's harder to detect. And so these general stages, you can also see like in Windows malware, there's some commonalities. So in Windows, you will sometimes write like, you can find custom PE file loaders, so you can load the file in memory and not have it on the disk for a second stage of malware. And in Android, they conveniently provide a function in memory dex class loader, and so you don't have to write it, it'll load code into memory for you. So that's super convenient. Some differences from Windows malware, well, is you have these categories on both: spyware, Trojan, backdoor, all the classics. But then you have some mobile specific categories of malware like toll fraud, call fraud, SMS fraud, ad fraud, things that, are easier to do on a phone. And so like toll fraud is when you go, if you're like on Verizon, like a really long time ago when some of us were alive, you could like buy ringtones and then it would just charge Verizon. And so you wouldn't have to like pull out your credit card. Well, toll fraud is kind of like that. And so they just try to do that automatically in the background without you having to click anything. So that's bad. Okay, so another problem we have when we're analyzing malware is time is money. So if the malware developer can just keep making the malware more and more complicated, regardless of the payload, eventually it gets complicated enough that you run out of time and money to analyze it. So it doesn't even have to necessarily be like a brand new obfuscation technique nobody's seen before, but if you can just stuff together more and more existing techniques until it's like, oh yeah, I actually might know how to reverse engineer this, but I'm just don't have the time. then that would be really sad. So we need to think of ways to like automate the deobfuscation process so that we can still do it quickly. Okay, exactly. So, and we're doing this, why we're writing malware is just so we can see how the obfuscators work and so we can detect it faster. So we're not releasing it, obviously. So thankfully, AI will write the malware for you. I wrote Android code for myself like a long time ago when they used Java, and Java has these beautiful type names and things, and now it wants to do it all in Kotlin. So I was just like, hey, please make something to access the contacts. And then you can just tell it, please allow me to back up the contacts to an external URL. And so it's just writing the malware for you. It doesn't even know. Okay, and then I had to understand the Android build system, which has gone through several iterations. I do actually think it's getting better each time, but when you Google for examples, it shows the wrong way to do it. So that's sad. Okay, so over here, this is the basic way to get contacts in Android. It's very simple. You query this database and say contact, easy to remember, and that'll do it. So, and then here's where we're gonna exfiltrate it. So here's the local IP. Obviously, you see people saying download my malware from 127.0.0.1. So that doesn't do anything, but that's just for testing. Okay, so we're gonna run the app. Sorry, I should explain the app. So it's just gonna look like your normal contacts. So list all your contacts, and it's just gonna send them to that local IP. So it's just very simple because I didn't want to take all the time for my research just writing the payload and then be like, I forgot to obfuscate it. Okay, so I really want to contact my friends Abe and Bob, and this is obviously contacts app, and you notice that when you open the app, Burp Suite will see the contacts are being exfiltrated, and then there's this Python script I found that just echoes all post requests, and so you can see they're being exfiltrated as JSON. All right, so we're going to reverse engineer this malware. This is just version 1. So here's the APK, and there's a very useful tool called Jodex, which is a free Android reverse engineering tool. And we're just, as I said earlier, we don't want to accidentally spend all of our time trying to reverse engineer something like the emoji library. So we're going to look for big pieces of data for like, what is the exfiltration URL? Okay, so can you find the exfiltration URL? There it is. It actually looks just as good as the original Java before we compiled it, because when you're just using the normal Java for the JVM, it has to keep all the type names of all the system libraries that it's calling. So there's the exfiltration URL. If only there was some way to make my life harder. So enter malware obfuscation. So what are some ideas we could think of? We could think of writing a custom obfuscator. That would be really fun, but that's hard. Or we could download a free obfuscator from GitHub. That's easy. And so what will malware developers do? They will usually just use a free one. That's really great because then you can also see the source code that they're using. Sometimes they use a custom one. Then that's really sad. We'll talk about that in the future. Okay, so now you might be wondering, I'm a malware analyst. I have limited time. I have limited money. And I have unlimited malware. So can I just say if it's obfuscated, it's malicious? No, because lots of apps obfuscate basically almost anything a malware could do. Application author could justify by saying, I need this to protect my intellectual property. So it's, lots of banking apps are obfuscated. You don't want people with rooted phones going in your banking app, trying to hack into the bank or whatever. So it's not inherently malicious. So we need to try to find what does the payload do. So I'm going to show you, this is a very common obfuscator. It's called string fog. And probably, depending on which version of the slideshow I downloaded, there's probably a diagram soon that shows how it works. Okay, so string fog is available in GitHub. There's nothing wrong with it. It's used to protect legitimate intellectual property. Here's how it works. You have original string. It generates a random key, and there's different modes. This is the default mode. It will base 64 the original string and the randomized key, and then it'll XOR them together, and then it'll automatically inject that obfuscated string and then that key in your program, and you'll see an example of what that looks like in a minute. Yeah, and to undo it, we just had to do that backwards. And so what's really convenient about this library is you just include it like in your Android build system, and then it injects all that code automatically. You don't actually have to change your code to say like string.obfuscate. It's all automatic. Okay, so there's where you can download it, and that's just a reminder. Android build system is very complicated. So here's basically what you do. This is it has some modules. So the default XOR. You can also enable AES if you want to make it really complicated. Okay, so there is actually an example project that just has the string fog build system and doesn't do a lot. So I stuck my app into there, and you see it looks exactly the same, except for now it's called string fog instead of context manager. And now, even though it looks the same, let's see what happens when you reverse engineer it. Dun, dun, dun. Okay, so now it's a little bit more complicated to use string fog. And I didn't have to type in all that code. Did it all automatically. This is the APK. This is not actually the Java, but obviously the Java will look very similar. So here's a little randomized string, and here's the key. And so if you just on base64 both of those and XOR them both together, then it will deobfuscate. So, okay, we need to actually find the payload because not everything obfuscated is malicious. Here's another example script. So, yeah, base64 decode, base64 decode, XOR. So, very simple. And you will see, ta-da, there's this exfiltration URL, and my IP kept changing because I kept restarting the, emulator or whatever. Okay, so that's really easy. So we want to think, that just like slows you down. It's not like, oh man, I could never reverse engineer this my whole life. But if you have thousands of strings with that obfuscation technique, and you don't feel like writing a script to do them all at once, and you're doing them one at a time, that could take a lot of time. But still, it's relatively easy to bypass. You just have to XOR everything. Okay, so we want to think, how can we make things more difficult? Well, we can obfuscate code using native code. Okay, and yeah, context manager 2 through 4 did not do what I wanted to, so we're on 5. Okay, use native code under analysis. Okay, so the way you include native code in Android is you say system.load library and then whatever the library name, and it'll automatically look in the Android /lib/ whatever the architecture is /lib, whatever word you put there, .so. And so it's just a SO file. And here's some more example code. If you just open an Android project and say create a native C++ project, this is the example code it gives you. So we're going to change it. Instead of getting the string like hello world from the native library, we're going to get our exfiltration URL. So I modified it. Instead of saying hello world, now I put the URL in there. And JNI is just a Java native interface. So that's how the Android Java and the Android C++ talk to each other. And so that's how you read the string. You just call the native library wrapper and then put that in the URL call. And that's just me using the obfuscated string. And there you can see the library is appearing in JADX, the reverse engineering tool. And now we're going to run it. And there it is. And it looks exactly the same. That's good. And we can see there it is being sent to Burp, and there it is being sent to the HTTP server. There's a bigger picture of the HTTP server. So working the same as all the other versions. So let's see what the code looks like. Now we'll use Ghidra, which is great. And there's where you can download it. And you can see, wow, it's so convenient. It already named the variable after the string. So there you see the string. So that's not super hard to tell what it does. It's just like you have to imagine if you're Android malware analyst, you just open up and look at the Java normally. Obviously, if you're like a Windows reverse engineer or Linux reverse engineer, you're used to always looking at the SO files. But if you're just looking at Java all the time, this could throw you off. So now you're okay, I found it. They got me. It was in the native code, but it's not obfuscated. So we need to make it harder. Okay, so now we're going to use, there's a couple of different native methods I'm going to show in screenshots here. So basically, you've heard of LLVM probably. So it's like a compiler building tool, basically overly simplified explanation. And then someone added a compiler pass to that to obfuscate strings and control flow called OLLVM. And then someone modified that to add some more obfuscation, and they called that ArmorRS. And what I did not realize at first is that was created using LLVM 3.19. So it does not totally work with my toolchain. But so we're going to have some screenshots of ArmorRS partially working, and then I'm going to show some custom obfuscation I did that is actually working. Okay, blah, blah, blah. And here's a sample file. So here's like what ArmorRS looks like. and it will replace sensitive strings with these wrapper functions, and there will be names of those wrapper functions in the data section of the program. And if you look at, there will also be a function named the same thing as those strings from the data section and data div, and you'll see, okay, we just have a bunch of random XORs, and some of these might not actually do anything, but I'll show you later the one that actually has the string that it's trying to hide. So, okay, a bunch of XORs, and we could undo those all manually, but you could imagine I'm reverse engineering a program with hundreds of strings. I don't want to do anything manually. Okay, and so there's this script to deobfuscate ARMRS, but it actually is written for ARM32, so I had to fix it to work for ARM64, and then now these screenshots are out of order. Okay. We'll go back to ARMRS in a minute. Okay, so now this is me just obfuscating stuff myself, so I made a program. Yeah, okay. Here's ARMRS partially working. Hold on. Okay. Alternatively, you can just write some obfuscation code in C++ and stick that into the native library. So I just XORed some strings myself, but I did it in native code. And I'll try to find the screenshot for that. Yeah, so here, so I just put XOR in the JNI code, and then it made it like, a lot more inconvenient because now you have all these nulls everywhere. There's part of the XOR key. There's a deobfuscation code. So obviously, if you enjoy reverse engineering, you can still reverse engineer that XOR, but it's just a little bit more inconvenient than having the obfuscation in Java. Blah, blah, blah. You can use Unicorn to like emulate this and run everything, but if you try to like jump to printf standard library call, it's not going to work. So you had to remove those. Okay, so, and here's the, let's see. Yeah, here's me modifying the ARMRS deobfuscation script to work for my custom XOR. And so it basically, you search for all the obfuscation functions in the obfuscation function list, and then you, let's see, you run it. So basically, sorry, I don't have the assembly up, but this is the register that the XOR result of my custom XOR code gets put into this register. And so you can just tell the emulator to run until then, and then read that register. And so that's the same result. So you can do that by hand, but now we can do it in an automated way. All right. I think that I have some slides disabled. Hold on. Well, anyway, that's enough screenshots, but if you want to see more screenshots of the other obfuscator, which is ARMRS, which works similarly, but it's just all automatic. You don't have to like go in there and type, oh, please XOR these two keys I made. It'll just make up a random key and then use a compiler pass to stick that in wherever you use a string. And so I do have some more pictures of that working, but apparently not here. So thank you so much. And if you have any more questions about Android, just let me know.